Hello everybody, I'm from Colombia. I will share with you my presentation. It's called Evaluation of the Physical Performance of an FTTH-GPON system for QuadPlay services after the incorporation of an radio over fiber module. I am the speaker, Andrés Felipe Escayón Portilla, and this research is with two co-authors, Víctor Hugo Ruiz Guacheta and Jose Giovanni Lopez Perafan. I am glad to be here in EDI CON China 2020. For me, it's a pleasure to be with you virtually. The abstract is related to that. This research proposes the design and simulation of a radio frequency module based on an orthogonal frequency division multiplexing OFDM system with quadrature amplitude modulation 16 QAM at a data transmission rate of 10 gigabit per second and a frequency of 10 gigahertz using the simulation tool OFDM. For that purpose, a fiber to the home FTTH gigabit passive optical network GPON triple play system, voice over data service at 2.5 gigabits per second, and digital cable television TV service with 16 QAM at 0.8 gigabit per second was designed in order to integrate a radio over fiber RoF module and offer quad play services, triple play plus mobile internet. Subsequently, the physical performance of the downlink of the FTTH-GPON system was evaluated after the RoF module was incorporated based on optical performance monitoring. OPM parameters such as optical receiver power, error vector magnitude, EVM, constellation diagram, signal to noise ratio, SNR, beer error rate, BER, quality Q factor, and I diagram. The results show that it may be possible for FTTH-GPON users to have, in addition to triple play services, a fourth one, mobile internet, because the quality of the mobile service is guaranteed with the last kilometer for access networks using the internet, using the current deployment of a standard optical fiber, demonstrating the feasibility of the proposed system. The contents I have for this presentation are introduction, theoretical framework, development methodology and simulation scenarios, results analysis, conclusions, and related research articles. We're from the University of Cauca, and we're happy to be here again. So the introduction, the revolution of telecommunications and technological convergence. It means that we have there is an efficient use of, or we need an efficient use of networks. Multi-service platforms, optical networks requires a higher bandwidth, services demand, final users, a higher rate, current access networks, the bandwidth is limited, and the wireless networks require a higher bandwidth and transmission rate are required, and the advantage is the mobility, and the RoF technology access network FTTH-GPON solution because because of the convergence between wireless and optical networks and the integration of XPlay services. The theoretical framework is based on these three topics: FTTH-GPON, OFDM, and the radio over fiber architecture. As you can see here, the FTTH-GPON is based on, I will explain this showing you these three images where you can see in the left corner, in the left top corner, that you have three triple play services and optical line terminal, and then you have a passive optical splitter where you can share the signals to all the users using a passive optical network. That is more precise in the next image, where you can see here the channels used, the lambdas used for reception and for downlink and uplink, and also considering to be able to insert more services. And at the end, you can see how this is deployed in the real life with a OTA in the end. And then you have outside plan with the passive optical splitter and the customer premises with video voice data using an optical network terminal. You can see here the 50 nanometer video over fiber is the red one used. downlink. For downlink, 1490 nanometers, the data and voice over fiber is the lambda use, and for the uplink, you have the 1310 nanometer data and voice over fiber. Then you can have also coaxial cable and the category 5 cable too, and also you can integrate WDM with solutions. Talking about the OFDM, you see here the OFDM transmitter. From left to right, you can see we have 6 components, starting with a pseudo-random bit source, data source. Then we separated the serial into parallel bits, and then you have the MQM here operating integrated with the inverse fast Fourier transform. And then you have the quad mix in order to take from the baseband to the carrier frequency, as you can see here, and then you have an electrical combinator to have the radio frequency output. And on the other side of the receiver is doing the complementary analysis, receiving the RF, and then you have a electrical splitter. The quad mix down is turning the radio frequency into baseband. Then you have some filters, and then you have the complementary process with a fast Fourier transform here. And at the end, you have the demodulator, the MQM demodulator, in order to have the serial, the parallel to the conversion from parallel to serial, and have the bit output for the users. Yes, you have here the RoF architecture. Is based on an RF signal receiver here, baseband modulator. Then you have the RF to optical converter using an optical modulator and using an optical source as a feeder. Then you have the optical link, and on the other side you have the optical detector and optical demodulator, the electrical demodulator, and at the end the system terminal. The development methodology and simulation scenarios that we use is based on a telecommunications equipment simulation methodology based on a conceptual model. We had a characteristic network as a model, some scenarios and parameters here, and 3 phases like the definition phase, development phase, and maintenance phase. The adaptive development and simulation methodology, it was based on a problem formulation with data collection and processing, then a conceptual model definition, then a simulation model formulation using experiment designs, then the simulation scenarios, also the model evaluation and estimated parameters using OFDM and MATLAB, at the end the data analysis to conclude with results and documentation. In the simulation design, we have like some 8 steps here in the left, a definition of test scenarios, obtaining test networks, logical and physical models, RoF module design, number 3, number 4, FTTH-GPON triple play network without RoF test. Then we have the RoF module test. The number 6 is the integrated network FTTH-GPON QuadPlay with the module, with the radio fiber module test. At the end, almost finishing results, comparisons, and the conclusions. And here you have the flow diagram for that, with the start, creation of the module conceptual model, then creating the network model, designing the simulation scenarios based on a theoretical fundament and parameter configurations, then executing and seeing if it is working, so we can conclude with observing and analyzing the results, and if they are coherent, finished, or else going back and testing until everything is perfect. The conceptual model, as you can see, is a reference simulation scenario taken from the following undergraduate project at the University of Cauca here in Colombia. FTTH-GPON topology impact on the triple play services performance. You see on the left the optical line terminal, then you have the optical channel, and then at the end you have the optical network terminal with triple play services. And we're going to use this as a reference in order to design the our RoF module, and then integrating this into the triple play in order to have the quad play scenario. The simulation module here is the triple play. As you can see in the left, we have the central office, we have the 3 services, then we have some fiber trunks, is roughly 20 kilometers, and then we can split that into It says here 32, but we used until 64 ONTs. So from the transmitter to the receiver. The simulations parameters used in the internet voice over IP service or data and voice service, transmission speed or rate 1.25 gigabits per second. The wavelength is the 19 nanometers and the S-band. Transmission power 70 dBms. Optical modulation type is external, and the receiver sensitivity is minus 27 dBms. In the digital cable television service, like the television service, multi-level modulation format, 16 QAM, transmission speed, 8.8 gigabits per second, carrier 1000 megahertz, optical module type is external, transmission power is 8 dBm, and the wavelength uses the 1550 nanometer on the C-band, and the receiver sensitivity is minus 16.3 dBm. Also, the parameters in the simulation we use is the laser as a continuous wave laser. The line coordinate was a non-return to zero. Modulator max sender. The optical fiber was a standard, I2T G.652. The attenuator was 1 dB. In the photodetector, the pin. And the electrical filter, a Butterworth with 16 order. And the optical filter was a vessel of the second order. In analysis, we can see here two results involving the FTTH-GPON triple play network performance parameters. Like in the left one, the picture A, we can see the voice or the data signal eye diagram, and in the part B we have the video signal eye diagram. The conceptual model that we use for the RoF transmitter was that we have a data source, then we have a radio frequency signal, 16 QAM OFDM, and then feeding that into an optical modulator that also receives a laser, and delivering this signal to the optical channel. And at the end, you can see the way the max sender, which was the optical modulator used, is working. The OFDM RoF logical block model is the one integrated to the triple play services I already mentioned. We have the OLT in the left, and at the bottom we have in the left the OFDM transmitter, also the laser, inserting this into the max sender modulator, and then putting this in the combiner in order to feed the optical fiber. And at the end we have the splitter, and we have the access network with 64 ONTs. The RoF simulation model, as you can see, the one that was proposed that we had at the first attempt was using phase modulation, but we outperformed this scenario. We changed that with an electroabsorption modulator here in order to have more distance coverage. The parameters used here for the RoF simulation was the transmission rate, 10 gigabit per second, 16 QAM modulation at 2.5 gigabytes per second. The inverse fast Fourier transform of OFDM module at 2.5 gigabyte per second. The number of subcarriers were 8. Cyclic prefix was 0.25 quarter. Delay was 0, and the radio frequency was 10 gigahertz. The laser frequency 194 terahertz, and the laser power was 0 dBms. Okay, so how the RoF module validation, we have here some pictures that show us in the left how the theory is and how we get that from the simulation. So it's very similar to the theory. At the end, after applying this at a distance of 5.860 kilometers, we have in this part here at the beginning, we have a back-to-back 0 kilometer consideration without distance. We have this constellation diagram in phase and in quadrature of the radio signal. Then we have in the letter B the measure at a distance, the measured signal at a distance of 5.860 kilometers. And the C one is the overlapping, ideal versus received. So we see that our performance is good. The simulation scenarios analysis of the RoF module before being integrated, independent. Then FTTH-GPON network analysis with integrated RoF module for single ONT, maximum distance or range. And at the end, FTTH-GPON network analysis with integrated RoF module for various ONTs, distance variation. The QuadPlay simulation scenario is the one that we had as a reference, the triple play, but then inserting at the end, we see here at the bottom left part, the OFDM RoF module in the transmitter part, then feeding it into the optical channel, and then we have at the end, at the bottom right, the OFDM RoF receiver with all the testers in order to see how the performance was behaving, varying the distance from 0 to a maximum distance of 6 kilometers, a little bit less, and then we have the conclusions of the data analysis of the results. So the impact when the RoF module is integrated into the FTTH-GPON network. So we made an analysis in terms of distance, then the physical, taking into account the physical optical performance monitoring parameters, improvement in the IVM, the error vector magnitude of the radio signal. We had an improvement because, or because it implies a better bit error rate. So that was the impact when we integrated this module. We had an improvement. And at the end, we had in comparison an additional 17 meters were reached on the link. So we had a better performance when we integrated this module into the triple play network. We have here the optical channel frequency spectrum for FTTH-GPON network services. So here we have the voice data, video, and also the radio signal within the optical fiber. So with the distance variation, we have the voice over data signal, bear versus distance, power versus distance, and the eye diagram versus distance, as you can see there. Also, regarding the video signal, is the same. We had two pictures here, the eye diagram versus distance, and the power versus distance. So we see that as long as the distance is increasing, so the power is decreasing. So we can see how the eye opening is closing. The distance variation with the radio signal is almost with the same behavior, power versus distance. We have the bear versus distance. It means that when we have more distance, reaching the 6 kilometers, so the error magnitude increases, and this is measured with the error vector magnitude here at the end. So we see that the error increases as distance increases. And finally, we evaluated the physical performance, or the purpose was evaluate the physical performance of the FTTH-GPON network by integrating the RoF module based on the optical performance monitoring OPM parameters using a simulation tool like OptSim and MATLAB. So the FTTH-GPON network with integrated RoF module for single ONT, optical network terminal. So we have here all the display of the scenario that we used, and if you see in the right part at the bottom, we have only one optical network terminal. We're going to replicate this, sharing this information or splitting this information up to 64 ONTs. So using one transmitter, one lambda for each of the transmitters in order to have like a DWDM in the optical channel. So the performance comparison of the FTTH-GPON triple play versus quad play network services for a single reference ONT is here in this chart. So we have in this table we see the service, voice, data, video, radio, and the fiber used, the standard, and also we used another one which is an improved version for dispersion, which is the Corning leaf. And we have the parameters, the triple play FTTH-GPON value without the RoF module, and the quad play FTTH-GPON value with the RoF module. So if you see here the parameters, bear, Q factor, and the receiver optical power, we have summarized what we got during the simulation. Okay. you see all the parameters that we measure over there. So the most important part to say here is that with the triple play, with the standard fiber, we reached 1,000 to roughly 1.3 kilometers, and with the corner leaf fiber, we had almost 6 kilometers. It's because this one is behaving better with the or in terms of the dispersion, but in the real life we have the standard fiber deployed, so 1.3 almost 1.3 kilometers. This is good for as a solution of the last mile or the last kilometer for the access networks. And here we're maintaining the performance. Okay. So the channel distribution DWDM for QuadPlay services in the FTTH-GPON networks, you can see here going from the ONT1 until ONT32 on the left, and in the middle until the 64, starting with the video lambda in frequency or the equivalence in frequency or in nanometers, until reaching the data and the voice. And from 1 to 64 is the distribution for the radio channels, because the video is fixed here and the data is fixed here, as you can see in the chart with the information. So the general model of the FTTH-GPON QuadPlay 64 ONT system is here. As you can see, it's very cramped. You have in the left, in the central office OLT, the triple play services, and the QuadPlay is with one transmitter for each of the lambdas that we're going to use in the optical channel, and also at the ONT in the access network, we can share that information one lambda to one lambda for any services that any user require in their premise. Like apart from triple play, we can talk about the mobile service in the mobile internet inside the house or inside the apartment or the building. So the total results corresponding to the test carried out for the case of several ONTs, if the distance is constant, the reference is one ONT. We started from 2 until 60 up to 64 channels, and the maximum fixed distance was 5.887 meters or 5.8 kilometers. So you see how the EVM is getting worse as the distance. If the distance is fixed, the EVMs is getting worse as the number of ONTs increases. OPM results on the FTTH-GPON QuadPlay network for 1 to 64 ONT with the distance as a constant is that in the QuadPlay, joint system performance warns due to destructive interference because of the number of channels, crosstalk, and somehow the fiber nonlinearities like the XPM and the FWM. And the distance must be adjusted, reducing it in order to guarantee the 4 services in all the ONTs present. So as if the maximum distance was almost 6 kilometers, so we're starting to reducing it until we had all the services with good quality. So the total results corresponding to the test carried for this case of several ONTs with the variable distance. So it's the same, but in the simulation we run 6 times or 6 different steps, like going from 1, 2, 3, 4, 5 until 6 kilometers, and we had the results in the next table. We perform an optimization. We force the system for the worst case in order to have the minimum acceptable performance, and then extract the value of the maximum distance reached between the OLT and the respective ONT to see if these results fit with the access network last mile or kilometer solution. So here you can see selecting the one for 8 ONTs from the number 1 to the number 8. All the running, all the simulations that we perform from 1, 2, 3, 4 until the kilometer the kilometer number 5, and we see the receiver optical power, the MBM in percentage, and the burr. So the comparison when we finished these simulations is like the FTTH-GPON QuadPlay network services for various ONTs specifying the maximum range. So you see numbers of ONTs going from 2, 4, 6, 16, 32, and 64, doubling the number in each simulation. So you see the burr and the distance. So the distance with the 2 or until 8 ONTs was like almost 6 kilometers, and then going down in the radio service from 6 to 3.8. And if we started to increase the number of ONTs, we saw that with 64 we had like 1.3 kilometers. So this is like the last kilometer solution that we are proving that is a good the study that we did proves that with that distance we can assure that this can be deployable in the real life. And the conclusions to finish is the criteria were defined for evaluating the performance of the FTTH-GPON network. Different simulation scenarios were analyzed and evaluated to determine the incidence of adding a fourth service, RoF, to an existing triple play network. The most important result, integration of the fourth service, RoF module, radio cellular telephone service, to the existing FTTH-GPON triple play network. And the RoF module, it had a positive impact on each of the services because each of the network performance parameters were improved to some extent, EVM, SNR, BER, Q-factor, and jitter. Regarding the simulation results, as the case is not ideal but real conditions, then the multiplexing process increases the incidence of nonlinear fiber effects and crosstalk, degrades system performance as the number of channels increases and or the spaces between them shrink. It is possible to affirm that this process of combination and separation of signal does not directly affect to the chromatic dispersion that depends on the transmission rate, type of fiber, constant of dispersion, the wavelength and distance, and to the attenuation that does not directly affect to the attenuation that depends on the type of fiber, constant attenuation, and the wavelength and distance. What was done was a sweep from 0 kilometers until reaching set reference distances, G, spaced each kilometer. Then when comparing the distance obtained from each particular channel, the channel J, it was obtained that when the distance was less than the particular distance, so the burr was less than T to the power of -3. So when showing that it was a good performance. In the limit, when they were equal, we had the regular performance, and when the distance is greater than this estimated distance that we get from the results, so the performance is bad because the burr increases more than the minimum. The related research articles I want to share with you is you can check them in order to go with further details about this research. The first one is already published, and the second one is still in peer-reviewed process in the IEEE Qualcomm 2020 for this year. I really appreciate your attention. If you have any questions, feel free to send them via email. You can reach me at afescallon@ieee.org. Thank you very much for your time, and I hope to see you in the next opportunity.